40. CPS Geometry. Pell's equation. Part 1. Approximating square roots. As stated in a previous video, the most important discovery, made by Pythagoreans, that is, as fundamental to mathematics and science, as is the Pythagorean theorem, is the discovery of the incommensurable quantities. In geometrical terms, this is encapsulated in the statement, the diagonal, and the size of a square, are incommensurable with each other. See the video, on incommensurables, if you want to learn more about this topic. This statement is equivalent to the following arithmetical statement: the number 1, and the number square root of 2, are two incommensurable magnitudes. In other terms, this can be stated as, the number 2, cannot be expressed by a ratio of 2 squares. Can we find another ratio, that can approximate number 2, very closely? How about subtracting 1 from x square first, and then, take the ratio? This can be extended to any, non-square natural number, n. For the general case, by doing this we end up with the equation x square minus n y square equal 1. This equation has been known since ancient times. Today this equation is known as the Pell's equation. Can this equation be solved? The answer is yes. But before solving it, let's look to another example where this equation appears. Part 2. Triangular square numbers. At a first glance at the close packing of spheres arrangement, two patterns stand out. These patterns have been already identified, in the first few videos of this series. The first pattern, corresponds to the plane, with an underlining hexagonal lattice. Triangular numbers are numbers, corresponding to complete triangular patterns, in this plane. The second pattern, corresponds to the plane with an underlining square lattice. Square numbers, are numbers, corresponding to complete square patterns, which can be identified in this plane. Two simple formulas, can be used to calculate the numbers of spheres, belonging to each pattern. Next, comparing the two patterns, one can observe that for some specific numbers, the triangular pattern, and the square pattern, contain the same numbers of spheres. A number, which is both, a triangular number, and a perfect square, is known as a triangular square number. Starting from this definition, and using the formulas characterizing each pattern, one can determine all the triangular square numbers. After some elementary manipulations of these expressions, one ends up with the Pell's equation, corresponding to n equal 2. Each solution of this equation can be then used to calculate the sizes of the triangular pattern and the square pattern. Part 3. Generating solutions, Brahmagupta's identity. There are two, apparently distinct, but in fact closely related problems, that have to be understood, for solving Pell's equation. The first problem is finding an infinite number of solutions, starting from one known solution. The second problem, more difficult to solve, is finding the fundamental solution, for any possible Pell's equation. Let's consider that one solution, to a given Pell's equation, is known. This solution is usually called the fundamental solution. You should be, by now, familiar with Brahmagupta's identity. If not, see the previous few videos which cover, in detail, this topic. Using this identity, one can show that if two solutions, verify a given Pell's equation, are known, then a third solution, can easily be constructed. Furthermore, this result can be applied when the two initial solutions are identical. In this case the second solution, and all the subsequent solutions, can be generated from one solution only, from the fundamental solution. Let's apply this method to the simplest Pell's equation, x square minus 2y square equal 1. The fundamental solution can be found by try and error, and is x equal 3 and y equal 2. The second solution is generated using the formulas proven above. One finds that 17 and 12 also verify the initial equation. Any number of new solutions can now be generated, using Brahmagupta's identity. 99, 70, and 577, 408, also verify the initial equation. This process can continue indefinitely. What can we do with these solutions? As shown in part 1 of these video, we can use them to approximate the square root of 2. By taking successive ratios of x over y for every new solution of the initial Pell's equation, one gets better and better approximations of the square root of 2. This method can be applied to any non-square natural number. In the context of CPS geometry, just remember, every CPS complex plane is determined by two orthogonal CPS lines, with units of measurements given by the square roots of some non-square natural numbers. The solutions to the Pell's equation, x square minus 2y square equal 1, can also be used to determine the triangular square numbers. The smallest non-trivial triangular square number corresponds to the second solution of the Pell's equation. X equals 17, y equals 12. Using the expressions established in part 2 of this video, one can determine the corresponding triangular number and square number. Of course, these two numbers are identical and equal with 36. The side of the triangle is 8. And the size of the square is 6. For the solution x equals 99, y equals 70, we get the next triangular square number, corresponding to a triangle of size 49, and a square of size 35. The total number of spheres in this triangle is equal with the total number of spheres in the square, and is equal with 1225. As stated before, this can be done for all solutions of the Pell's equation. Part 4. Finding the fundamental solution, the seed. As said before, finding the fundamental solution for some Pell's equations proved to be a more challenging problem. Next, we will provide a general method for solving this problem. This method was discovered by two Indian mathematicians. First, Brahmagupta, in the 7th century, found a derived equation associated with the Pell's equation, which, once solved, provides the fundamental solution to the initial Pell's equation. The derived equation is obtained from Brahmagupta's identity, when considering the two right factors in the identity as being identical. By doing this, one will observe that the term k can only have one of the following values, plus or minus 2, or plus or minus 4. The second Indian mathematician, Bhaskara, in the 11th century, has found a way to reduce the derived equation, through few iterations, until k ends up with the desired value. This method works for any Pell's equation. The number of iterations, or better said, the number of steps required to get to the final form, depends on the number n in the Pell's equation. The best way to understand this method is to apply it to an example. Part 5. Hands-on example. Let's apply this method to one of the two problems, mentioned by Bhaskara himself, in his book written almost 1,000 years ago. Tell me, friend, if the method of generating squares encompassed your mind, as completely as a hanging plant encompasses a tree, what are the squares, which when multiplied by 67, and added to the unit, produce squares? Solving this problem requires solving the following Pell's equation: 67x square, plus 1, equal with y square. The derived equation, corresponding to the initial equation, has the following parameters: a equal 1, b equal 8, c equal 67, and k equal -3. Due to the fact that k is equal with -3, we need to apply Bhaskara's lemma. The value of m can now be determined by looking for the solutions in integers, which satisfy the following two conditions. 1. M plus 8 divided by -3 is integer, and 2. M square minus 67 has the smallest value possible. Substituting m equal with 7 in the Bhaskara expression, after some elementary calculation, we end up with the new expression for the derived equation. 67 multiply by 5 square plus 6 equal with 41 square. The parameters corresponding to this derived equation are a equal 5, b equal 41, c equal 67, and k equal 6. Due to the fact that k is equal with 6, we need to apply Bhaskara's lemma again. Let's substitute the new parameters in the same expression. Again, the value of n can be determined by looking for the solutions in integers, which satisfy the following two conditions. 1. 5 multiplied by n plus 41 divided by 6 is integer, and 2. N square minus 67 divided by 6 has the smallest value possible. Substituting n equals 5, we get a new expression for the derived equation. 67 multiply by 11 square minus 7 equal 90 square. The parameters corresponding to this derived equation are a equal 11, b equal 90, c equal 67, and k equal -7. Now k is equal with -7, so we need to apply Bhaskara's lemma again. Substituting the new parameters in Bhaskara expression, we finally end up with a value for p, which generates a derived equation where k equals -2. This derived equation has the right form and can be used to solve the initial Pell's equation. We now have a equal 27, b equal 221, c equal 67, and k equal -2. By substituting these values in equation 3, and then dividing by 4, we end up with the fundamental solution to our initial equation. 67 multiply by 5967 square plus 1 equal 48,842 square. Starting from this fundamental solution, x equals 5967, y equals 48,842. And using the method described in part 3 of this video, one can generate an infinite number of solutions.